Continuing on. Now that I was done with that rude interruption. The earthquakes send waves to go through the earth, much like those nudie scanners in the airport. You stand like this, and they're sending waves that are going through your clothes and bouncing off your body. Well, I call them the nudie scanner because they're looking at your naked body, even though you're wearing clothes, because different things interact differently with the waves. So it's the same type of thing for the earth. We have waves that go through the earth. We call them seismic waves. And these seismic waves travel at different speeds in different types of material, just like waves travel at different speeds in, light travels at different speed in water than it does in air. And just like light waves going through from air to water, the waves will bend as the speed changes. Furthermore, we have two fundamentally different types of waves. Remember from physics, we had transverse waves and longitudinal waves. Longitudinal waves is where the displacement is in the same direction the wave is traveling. Transverse waves, the displacement is perpendicular to the direction the wave is traveling. Well, they have different speeds for those two waves. So you have an earthquake that occurs in one place on the earth, and the waves will have different speeds for the two types. So if you have a measuring station and you measure the waves, you'll have a time gap between when you receive the faster one and the slower one. And knowing the speeds of the waves and the time gap, you can determine how far away it was. And then they do a lot more work to figure out how the speed was changing. And that's how we get this picture. So it's basically like they're taking an X-ray of the Earth, but they're using seismic waves rather than X-rays. So we have pretty good confidence that this is what's really down there. So underneath that crust, there is the mantle. The mantle has two pieces, the upper mantle and the lower mantle. In between is what we call the SCNC. The upper mantle, the crust, forms tectonic plates. How many people have heard of plate tectonics? Okay, good. We've all heard of that. Plate tectonics is something that's occurring with the crust and upper mantle. There are pieces that are acting like, well, the best explanation I know of is treat it like an eggshell. It's like the Earth's crust and upper mantle is like an eggshell. The egg's been dropped, it's hard boiled and dropped, so the eggshell is fractured everywhere. And then there are forces that make them slide and move relative to each other. And so the motions are what causes things like our earthquakes. And I think we'll talk about that more. But underneath the crust, we have this mantle, and the mantle is fairly uniform. And I know it says mantle, but it's just easier to write it there. Fairly uniform. That is, it doesn't matter where you are in the mantle. If you're the same distance from the core, it's going to be pretty much exactly the same environment. As you get deeper, of course, the pressure is increasing. What causes the Earth's air pressure? The air pressure you're feeling right now. I think we even had this on our first test, didn't we? Air pressure. What's causing it? Yeah, gravity. It's the weight of the air above us. So if you go into the Earth, of course, the Earth is much more dense. So the weight of the Earth above you increases much more dramatically as you go down, which means the pressure has to increase very dramatically as you go down into the Earth. So you go down there, the pressure is really increasing, and the temperature is really increasing. Why is the temperature increasing? There are two reasons we believe for that. One is radioactive decays. Radioactive decays, we've learned, they release energy when you have a radioactive decay. Radioactive materials here in the core are still releasing energy, heating up the core. We also have the Earth is cooling. Over time, the Earth will cool from when it was formed. Based on the scientific understanding, this may not be yours, that's fine. Based on scientific understanding of the Earth, when the Earth originally formed, it was all melted. And the outer part has frozen, but the inner part is still cooling some. So we have a couple reasons why it's hotter down there. So you get deep enough, and you have the liquid core. Now that's liquid, swirling liquid. You go even deeper and you have the solid core. Now you might really wonder, how do we know there's a liquid core? How do we know there's a solid core? Not going to go into the waves real carefully, but it once again comes from looking at those seismic waves that we understand there's a solid core. Another question you might have is, okay, when it's really hot, things melt. And inside of that liquid core, it should be super hot. So how do you have a solid in there? Because the pressure is so high, it makes it so it solidifies even at that very high temperature. So it's because of the excessively high pressure that you have a solid core inside the liquid core. So that's what we understand our Earth to have. You might ask, why is that important? How many people have thought that? Why is it important? Okay, Gabby and Ashley. For the two curious minds, here are some reasons. Reason number one, the Earth behaves like a magnet. Why does it behave like a magnet? From all of the studying and all of the computer modeling, right, we can't go down there, so we have to use computer modeling. The Earth behaves like a magnet because that liquid core is going around and it has the temperature differences, which causes what we call convection. Remember, we talked about convection. You see a lot of things we learned in physics have already come up. Some things we learned in chemistry have already come up. The convection, along with that swirling, creates magnetic fields. And so the Earth's magnetic field, what we call the magnetosphere, is the result of this liquid core going around. Now here's some other bizarre things about it. The sun has a magnetic field, and we believe the sun's magnetic field is a similar thing. The sun has, instead of water, that's not water, that's molten iron, we guess. We guess it's molten iron because more dense things sink. Iron is 1/3 of the Earth, and it's very dense. Hence, you expect that's mostly iron down there. Not purely iron. Certainly there's gold, because gold is much more dense than iron, but predominantly iron. The sun, we believe it's actually hydrogen that's swirling around, making its magnetic field. But when you look at the sun, there's some crazy things that happen with the sun. The sun's magnetic field flips. The north pole of the sun becomes the south pole about every 13 years or so. That's kind of crazy. Well, our understanding is that that's because the magnetic fields created by all that swirling, in this case hydrogen, starts kind of get tangled up and cause the swirling to change directions, and that's what makes the flips happen. If the Earth has a swirling material making its magnetic field, then should the Earth's magnetic field flip as well? Logically, you would say yay or nay. Yeah. And in fact, we have evidence that it has in the past. Looking at the ocean floors, mariners noticed when they started using compasses as devices to navigate, that when they were going over the ocean, some places the compass would do crazy things like this. Spooky, right? If you read about the history of magnetism, magnetism was considered a spooky thing. And of course, scientists, we've learned the scientific method. It's going to come back in the final exam. We're going to have another question on that scientific method. The same, not the same observation, everything else the same as you had in the first exam. And so here's something really interesting. Notice that the compasses are doing things like this, changing as they go across the ocean. And so the scientist is like, why could that be? Well, there must be, and they come up with their hypotheses. And then after you come up with a hypothesis, what's the next step in the scientific method? You have to test the prediction of that hypothesis. So along the way, they've gone out and they've tested the ocean floor. And what they found is the ocean floor has magnetic materials, has minerals that have magnetic properties. And there are bands where they have north is pointing that way, and then bands where north is pointing this way. They change back and forth. And by looking at that, they have determined that the Earth's magnetic field has changed poles many, many times in the Earth's history. So we do change poles. And in fact, right now, there's some pretty significant anomalies occurring in the Earth's magnetic field. Some people are worried maybe we're close to a flip. Why would that worry anyone? That magnetosphere is important. It deflects radiation from the sun. And so that losing that magnetic field for some period of time means we'd get a lot more radiation, a lot more mutations, a lot more cancers. There's just a little bit of how this is useful. Other things are trying to understand how earthquakes happen, a little about the history of the Earth, and it helps us to understand other planets. If we understand our planet, the one that we can see, then we can look at other planets and use our scientific knowledge here to make hypotheses about what's going on there. As far as the size of the Earth, so here you can see the more details I was talking about. The upper mantle and the crust is together called the lithosphere. So this here together is the lithosphere. Litho means rock. Excuse me. So that's the rock region. Then we have the lower mantle and the that's right. And then we have the outer core and the inner core. You can see the sizes. The lithosphere is about 100 kilometers thick. Actually, I made that too big. It actually shows lithosphere right there. The continental crust is 30 to 40 kilometers. Continental, that's where we are. We're on a continent, North America, as it turns out. The oceanic crust can be as narrow as 5 kilometers. So when scientists try to drill through the crust, they're obviously going to go to the ocean because it's much less they have to drill, but still they haven't made it. There is, I believe, another effort ongoing right now. Then you have that lower mantle is pretty big. The core is pretty big. There's the Earth. Good you know. We're obviously not done. We're like on slide number 3. Now, previously I had 8 elements is 98% of what? Of Earth's mass. This here says oxygen and silicon make up 75% of the Earth's crust. Mass of the entire Earth versus mass of the crust. Remember, iron was 1/3 of the mass of the Earth. But in the crust, where's iron? It's only 5%. Why is iron only 5% of the crust if it's 1/3 of the Earth? Okay, it's more dense, so it is sunk to the lower areas. So it makes sense. Oxygen and silicon must be less dense, specifically in the silicates, and so they floated up. So oxygen, silicon, really important in the crust. You might notice the ratio here. That's about 2 oxygens for every 1 silicon. We'll see a reason for that. Now we have our definition of minerals. Remember I asked, what are minerals? We had some real unclear, uncertain answers. Well, first, these minerals are things that occur naturally. And they're crystalline solids. Who can name a crystal? Anyone? What? I'm just not hearing.
No, it's not ozark.
Never mind. Well, okay. If you look in here, there's lots of examples of things that are crystalline. This is just a magnifier. It's a box. Here's what most people think of as crystal.
Yeah.
This here, I believe, is the calcite crystal. There's lots of different types of crystals. That's a type of crystal. This here is a different type of crystal. This here, I think, is galena. There's a key up there. Yeah, I know. I'm over here. You should come over to the other people and take a look. There are different crystals. There are things that have a repeatable structure. So when you're looking for a crystal, this is what I said it looks like again. You're looking for things that you can see there's planes where it fractures on, and it has a certain shape that repeats. This is the one that I think is calcite crystal here.
Quartz.
Quartz is another crystal. That's what most
That's what I
people
was
think.
thinking.
Most people think of quartz when they think of crystal. People who believe in the power of the crystals, the healing power of crystals, they exclusively go to your gemstone type crystals. But another type of crystal you have is iron. I'm not sure what the healing powers are of iron, but hopefully those are really high because you got that all everywhere.
Iron is a crystal?
This is not a crystal. This is, you know what this is going to be. Obsidian. Obsidian, of course, when I was a kid, we used to go looking for the Indian arrowheads when we went camping because the Indians used them for arrowheads because they were smart people. It makes very sharp edges when you fracture it. Why? Because it's a glass. Glasses are not crystal. They don't have a repeating structure. And without that repeating structure, they fracture differently and give you sharp edges. So some of these things, if you look at this, you see that there's like that little rectangular thing, and then it's in this pinkish stuff. You have a bunch of those. What you have are different types of crystals in here. Each of the different type of crystal is a different mineral. So that's what the minerals are here. They're the different naturally occurring crystals. So this one here, you see a lot more different types of minerals. You have some feldspar, some, I can't name them all because I'm actually not a geologist. So these are raw samples. I'll leave them up here, and you can look at them at your leisure as you're leaving class. Here's the key that tells you what each one is. So you can say, was he right? What was number 11? Yes, it's Helena. I was right. So minerals, crystalline solids, repeatable structure. That means if you question.
Is it marble? Is that a crystal or is that a type of crystal? Isn't that like
Marble is a metamorphized calcite, or limestone, if you will. It's calcium carbonate that has been metamorphized. We have 3 fundamental types of rock. This is within the realm of today's lecture, so I'm just going with what you said. 3 fundamental types of rock. You have igneous rock. Igneous rock is rock that has been molten and then frozen. So this here shows some examples of igneous rocks right here. Granite is an igneous rock that cooled very slowly. If it cools slowly, you have time for crystals to grow. Crystals grow because you have one atom, and then another one comes, and then another one comes. They start forming a structure that has repeatable spacing based on, hey, it's lower energy if I go here. And then more atoms come and it grows and grows and grows. So crystals grow, but it takes time. So if something cools really slowly, those crystals can get bigger and bigger so that you can see them with your eye. And so granite, you look at granite and what you see is a whole bunch of different crystals. If you look carefully, it looks like kind of like salt and pepper when you look from a distance, but you look up close, you say, yes, there's a little black mineral, there's a little pink mineral, there's a little quartz is very clear, it's transparent, clear mineral, as you can see the different minerals. If it cools more quickly, then you're going to have smaller crystals. And so basalt, which is actually not in my thing there, let's see. Yeah, I don't have basalt on this. But basalt, this should be basalt, I think. Nope. Yeah. Let's go with this one there. Okay, that's ample. Well, basalt is the same elements as you have in granite, but it cooled more rapidly so you couldn't grow big crystals. So if you look at it in a microscope, you might be able to see the little crystals of the minerals, but they're not big enough to see normally. And then the obsidian, same chemical composition again as granite, but it cooled so rapidly it didn't have time to form crystals at all. And so it looks very different. So those are those are the igneous rocks. You have, that's usually where I start the rock cycle. You have molten magma, comes up out of the earth, freezes, giving you those three types. Then you have the processes of changing rock. Two different types. One is metamorphosis. The metamorphic rocks are subjected to high pressure and or temperature, usually with some water involved. And so it causes them to kind of squish. It's kind of like you take the rock and you put it in your toothpaste tube and you squeeze it out. And so it gets deformed. That's what marble is. It's calcite that has been put under pressure and heated, not melted, but deformed and squished about. So marble, because it's calcite, the calcite we've actually seen in lab, and we had a question on the test about how limestone neutralizes acid rain. It dissolves in an acid. And so your marble statues, because they're calcite, that's their basic mineral, they will dissolve in acid. And since water has some acid in it, rain will dissolve them over time. Or a marble countertop, over time, it would be susceptible to some loss due to water. And if you did something, I would say silly, but it's not. Something silly and you had acid on there, it might dissolve rapidly. How would you have acid in your kitchen? We did a lab on this. How would you have acid in your kitchen? You know what? I don't remember if that was acidic or basic. I thought it was basic. But there are things that we use all the time that are acidic. Things like, I don't know, I'd love to have me some pineapple. Well, that's pretty acidic. Or orange juice. You slice the orange and make some orange juice, you spill some orange juice on that marble, it's going to have some dissolving effect right there. Right? So marble countertops for kitchen is probably not the way to go unless you have a coating on it that's going to be protecting it from the elements. Okay, now, I've talked about two of the three, so let me finish it. Sedimentary rock is the third type of rock. Sedimentary rock is the kind of rock that results from weathering, erosion, transport, and then deposition. The sedimentation cycle, and once again, this here has some sedimentary rock samples. The sedimentation cycle starts with weathering. Weathering is something breaking up a rock. What's breaking it up? Well, it could be, like in the case of calcite, it could be an acid dissolving some of the rock. Or it could be people walking on the rock, breaking off little pieces. It could be as simple as yesterday my son was asking why the potholes are so stinking big here in Lincoln. I said, well, it's because it's not cold enough to stay frozen all year, but it's not warm enough to stay thawed all year. And so what happens is water gets in a crack, overnight it freezes, it expands, and breaks stuff. During the daytime, it thaws, it melts, refills in its new bigger volume. At night, it freezes, makes the crack bigger, and that's another process of weathering, or actually of erosion. Weathering then is a transport process. I gotta get the word straight in my head. I think weathering is the breaking up, and erosion is transportation, moving it from point A to point B. So the reason you're not supposed to walk off of the paths, like if you go down to Holmes Lake, there's lots of paths that are just going down the lake. Well, you're not supposed to use those. They put asphalt on one so that it's not going to be moving the dirt when you walk, but you're not supposed to go down there because you're going to be transporting dirt down, making it so eventually you have a basin there and you'll have to fill it in. Well, that stuff goes, it might get into water and flow in the water, but eventually it gets dropped somewhere. And so that's sedimentation when it gets dropped somewhere. And then you finally have cementation. If you compact this sediment together, it will form a solid. And so your sedimentary rocks are things like over here, where, well, you have, well, okay, that's metamorphic, that's sedimentary. These are all sedimentary here. Conglomerate means that you have a bunch of rocks that have been rolled, so they're kind of smooth rocks that have been cemented together. And then you can have sandstone, that's sand that's been compressed together. Mudstone is not shown here. Mudstone is sand and silt that has been cemented together. Shale is silt that's been cemented together. So those are the last type of rocks, your sedimentary rocks. So we have the rock cycle different. Obviously, it wasn't what I have in my next slide, but you asked a question. I went there, and now we're out of time. I will end with this. Minerals are classified by their chemical composition. Each mineral has a different formula for the chemical, and by their crystal structure. Each one's going to have a different structure. And so here's just some examples of minerals, and we'll talk more about these minerals next time. You might notice this here. That is a streak plate. If you look in the little rock box, there's a streak plate, something that you can rub your mineral on and see what color it actually draws. And you see in this example, the black mineral draws in a red, and that tells them about the mineral composition. Okay, so have yourselves a great, today's Wednesday, right?
Like minerals are classified by what?
Well, the one before we had their crystal, their chemical composition and their crystal structure. And then here's the physical properties we measure for them.
Wow.
That is speaker wire.